This one will be a relatively short video, but it's got some important ideas in it. Right. So far, we've met up with the idea of the wave function, right, and the Schrodinger equation as a route to obtain the functional form for our wave function. We also talked about the fact that we can use the square of the wave function to tell us something about the probability of finding the particle, right? So the square of the wave function gives us the probability density function. In order for that to work properly, we need to make a little bit of an adjustment to our wave function, okay? And this is what's called normalizing the wave function. So the probability density is the square of the wave function. So psi squared is that probability density function, which means the probability of being between x and x plus dx is given by the expression here, just psi star psi times dx, all right? If we take that over all of the possible values of x, it should make sense to say the probability of the particle being somewhere in the universe of available x values has to be equal to 1, right? If my wave function is going to describe an electron, for example, that electron has to be somewhere. And so the sum of all of those probabilities should be 1. Because our x variable, our position coordinate in general, is a continuous variable, that says that what we want to do to sum over all those probabilities is to take the integral of psi star times psi dx and force that to be equal to 1. All right. So the range of our integral here will be just all the possible values of x, depending on how we set up our coordinate system and what the terms of the problem are. That might be from 0 to infinity. It might be between 0 and some finite boundary. It might be from minus infinity to infinity, right? But whatever are the range of x values that make sense in the context of the problem, that's what we're going to do the integral over. When I do this, what's going to happen is if this integral is not equal to 1 naturally, then I'm going to multiply the wave function by some constant in order to force it to be equal to 1, right? So we're going to introduce a normalization constant such that the integral is definitely driven to be equal to 1. Right? The best way to illustrate that is probably just with a simple example, okay? So suppose we take a wave function that just looks like this. It's kind of an unusual wave function. It's just a sine function, right? And it says, in this case, our wave function only exists for values of x between 0 and pi. So that's going to be my range for this. In order to normalize this wave function, what I need to do is I want to say, let's say I set up the integral of the wave function, right? So if I take my wave function as just sine of x, then my integral of psi star psi dx is just going to be equal to the integral of what's going to be sine squared x dx. And I want my integral to go from 0 to pi. Because that says that's the only places where the wave function is non-zero, right? If I integrate over other x values, I'm not going to get anything else contributing to my integral because the wave function is 0 everywhere else, according to that statement, right? If I take this and just look up how to get a value for that integral, okay? You could, if you go back, if you were still in your calculus classes, you could probably force your way through doing that. It's been a long time since my calculus classes, and so I'm a big fan of looking up the integrals. And in return for that, I wouldn't be expecting you to be doing an integral that was terribly complicated without being able to look up the form for it itself, right? But it says here, the integral of sine squared dx, sine squared x dx is just supposed to be equal to 1/2 x minus 1/4 sine of 2x is what my notes say, right? So I need to take that and evaluate that at 0 and at 2 pi, at pi rather. And if I do that, what am I going to get? I'm going to get a pi over 2 from the first term, right? I get pi over 2, I get minus 1/4 sine of, it says 2x, so I get 2 pi there. And then I get those things, I get minus 0, and I get, let me do this, let's call that minus 0 and minus 1/4 sine of 0. Sine of 0 and sine of 2 pi are both themselves 0. So those go away. And that means all that is equal to pi over 2, okay? So my normalization condition says I need this integral to be equal to 1. Right now it's equal to pi over 2. So what that says is I need to multiply the integral itself by 2 over pi. That means I need to multiply, and the integral is the integral over psi squared. So I want to multiply psi by the square root of that, right? So this thing, I'm going to say I needed a normalization constant that would be out here. If I take some something that I'll call, say, a squared and put it out here, right? This thing will force that integral to be equal to 1, okay? For that to be true, I need a squared to be equal to 1 over this. So I'm going to have, I'm sorry, I've done that again. I'm going to have a squared is equal to 2 over pi. Really, I don't want to do that. And that means that a is equal to the square root of 2 over pi. Which means my wave function then looks like the normalized wave function psi of x is now equal to square root of 2 over pi times sine of x. Right, where that's the value as long as I'm in the interval here, and my wave function is equal to 0 every place else, right? So with that constant in front of there, now I have a normalized wave function. So now I can properly interpret my probability distribution by taking psi squared. That's what it means to normalize a wave function, is to make sure we have the appropriate constants in front of things to make that integral have its value be forced to be equal to 1. I put in here a problem. This is a sort of problem that, gosh, if we were having this class in person, I often do little questions like these with the clicker systems. But this is kind of a useful one to pin down some of the ideas that we're looking at right now. So I thought I'd go ahead and talk my way through it. If you want, you might pause for a second here and just give yourself a minute to think things over and decide what you think you would do to answer the question, okay? So I've got a wave function plotted there, and it's a sort of a random looking thing because frankly, it's just made up. But it's plotted as psi of x versus x, all right? And it says we want to find the probability of being in a range between 0.2 and 0.3, all right? If I want to do that, I need to remember that my probability density function, my probability function is about psi squared. What I've got right now is psi of x, not psi squared. So the first step in solving this problem is to take my wave function and square it. If I do that, it's kind of friendly because it's only got a whole number of values everywhere, and that makes it pretty easy to square, right? So if I take this and square it, here I'm going to have, well, I'm going to have 1, so already I went astray. 1 squared is not 2, is it? So let's erase that and try again. I've still got 1 down there. Up here where the wave function is 2, when I square it, those values are going to go up here to 4, right? And then I come back down, I get 1 again. So next thing I have to do is I have to check and see if my wave function is normalized or not, okay? If I take that, I want to do the integral over that, and I can do that by just counting boxes, essentially, right? So if I count down here, this is a 10th across each one of these little squares. If I map out this square here, each one of those little squares is got an area of 1/10 because it's 1 for the height and a 10th for the width, right? So I've got 4 squares across the bottom. That's 0.4. Here I've got 0.5, 0.6, 0.7, 0.8, 0.9, and 1. So my wave function integrates to, my wave function squared integrates to 1. So my wave function is normalized, okay? Then it says, I just want to find the probability of being in the range from 0.2 to 0.3, right? Of the total area under that function, which is equal to 1, how much of it is in that window, right? That says I'm now looking at this part here that I'm shading in. If I do that in that column, I have 4 of those boxes. Each one of those boxes has an area of 1/10, we said. So I have 0.4 out of the total area of 1. So my probability of being in there looks like it's 0.4, which means I could say there's a 40% chance of finding the particle in that region if it's represented by this particular wave function, okay? There's a little bit of trickiness in there because we do have to check and make sure the wave function is normalized, meaning that the area I got after I squared it was equal to 1. If that wasn't true, then I could either imagine putting in a normalization constant, or I could have just divided the area that is under that region by the area under the entire thing to get the probability that way, and that also would work. Okay, so that's a nice little sort of conceptual question, way of doing some of these things without doing tedious math, and I do like things like that. So when you get to your first quiz and exam, you should be prepared for some questions that will, like that, try to focus just on your understanding of what it is that we're trying to do in the sort of peeled away from things like doing integrals and all that. So there are a few other conditions that a wave function has to satisfy. We're not going to go into detail about all these. We're just going to give us a quick little list here. We will invoke some of these at times to help choose appropriate wave functions. Okay, the first one is the wave function has to be continuous. Okay, across whatever range of values are valid for the problem, I have to have a continuous function. The first derivative of the wave function also has to be continuous, it turns out. Okay. It has to be single valued, meaning for a particular value of x, if it's a one-dimensional problem, at any given point, there can only be one value of psi, okay? Because otherwise I would have more than one probability of being at the same point, and that can't actually be right, okay? The value of psi itself must be finite, okay? And that's in part because we have to have it be so that the square of the integral of psi squared can be equal to 1. If psi itself can go to infinity, then that is not going to work, right? In a lot of cases, these restrictions will lead to the fact that only certain solutions to the Schrodinger equation are allowed. This is where quantization comes from, right? The fact that some wave functions are valid and some are not. And that's what gives us some limited number of possible states, right? These arguments are what leads to the fact, for example, that if I take a hydrogen atom, that it gets certain orbitals that have certain energies, and the electron in that atom can't take on any other energies but the ones that correspond to those states. Okay, so these rules are essentially giving us boundary conditions, and those boundary conditions are what lead to the idea that things become quantized in these kinds of systems. All right. I want to introduce one more idea about how we can get information about measurable quantities from wave functions, okay? And that is the notion of the expectation value. All right, so expectation value is a phrase in quantum mechanics that says even for things where the wave function is not an eigenfunction of a particular operator, we can still often get some information about what to expect if we measure that property. Okay, so the expectation value, as it says there, is the average of a large number of measurements of the quantity that's represented by that particular operator, right? So if I take an operator A and I measure property A lots and lots of times, and the limit of very many measurements of that quantity, the value that I get, the average of all those measurements, should come to the expectation value of this operator, okay? In the previous example, that's referring to the end of the previous video, actually. The single value for the momentum would not be determined, right? And I said at that time that in the free electron case, that we would have the linear combination we made involve the particle being able to go this way or go that way, right? And so in one case, the momentum is plus a quantity. In the other case, it's minus that same quantity, right? So if I measure the momentum over and over again, each time I measure it, I'm either going to get plus or minus that momentum, right? But if I take lots and lots of value of measurements, because the two cases are equally likely, the average of all those measurements is going to be 0. That makes 0 the expectation value. It's a little bit interesting because in this case, if you measure the momentum, no individual measurement of the momentum would ever give you the value of 0. Right? You'd always get either plus or minus the quantity that we got when we did that momentum operator. right? But if we take lots of measurements and take the average of them, we're still going to get 0. Okay, and that's a little bit of a curious result, but it's sort of like saying if you if I take the average score for an exam given to a large class, even if all the individual scores are whole numbered values, the average is generally not going to be, right? And that's because it's the average of lots of measurements. It's not any one of those individual measurements, okay? And that gives us a tool for finding the expected physical outcome for things that are not actually where the function is not an eigenfunction of the operator, all right? How do I calculate one of these expectation values? It's a reasonably simple expression, right? So this notation here, the angled brackets, that represents the expectation value for property A, all right? And so whenever you see those brackets around something in the context of quantum mechanics, that's an expectation value. I'm assuming my wave function is normalized. To get the expectation value, what I do is I want to take the wave function of the complex conjugate and I want to sandwich them with the operator in between. Okay, I take that expression and I integrate it over all the possible coordinates, right? So if I'm still doing a one-dimensional problem, I'm going to integrate this over all the allowed values, in this case of x. All right. What I'm going to do is I'm going to use this this formula here, or this definition, to find the expectation value for the momentum of the particle described by our sine function, the one we had moments ago. Okay, we have our momentum operator, right? And so let's go ahead and do this. My momentum operator, I need to remind us what that is. If I say, I'll just do it up here. I have p hat is my momentum operator, right? And that's equal to h bar over I and a derivative like that, okay? That's my momentum operator. So if I want to use that to find this expectation value, the first thing I want to do is I really should be putting in my my normalization constant. I'll drag that back into the problem later, I think, because I don't have it written in the notes that I have here, and it actually won't matter in the end. So my expectation value says I want to take the integral over all the plausible x values, which is from 0 to pi, right? And I want to integrate psi star momentum operator psi dx, right? Now I'm going to put in what my operator is. So this is going to give me h bar over I out here. And then I've got my integral from 0 to pi. And I've got sine of x. And then I have the derivative sine of x dx. That's going to be integral of h bar over I 0 to pi. What do I get? I get sine x cosine x in there. Okay. If I take that integral, I will tell you that my notes over here tell me that this piece, the integral of sine of x cosine of x, that will give me sine squared x over 2. Right. I'm integrating from 0 to pi. It turns out that that means evaluating that thing at both limits. Sine of 0 and sine of pi are both 0, right? So my integral is 0 at both of those limits, and that tells me that my expectation value for the momentum here is equal to 0. Right? So that says this is a case where if I measure the momentum lots of times, I should end up with the average of all those values being equal to 0. Okay, we can do this for any sort of operator for any property, right? If we do this formalism, if we take that sandwich integral around an operator where the operator, where the wave function is an eigenfunction, then we're just going to get the eigenvalue, right? Because if the wave function is an eigenfunction of the operator, then every time I measure it, I'm supposed to get that eigenvalue. But this lets us predict what should be the outcome of measuring properties where the wave function is not an eigenfunction of that particular operator. So it's a powerful tool for predicting what should happen in actual measurements of these observable quantities, okay? Summary of what we expect to happen when we take measurements, right? If the wave function is an eigenfunction, then the eigenvalue is the corresponding measurable value, right? The easiest example of that is just the energy, right? Where we say h psi is equal to E psi. So the energy for a particle described by wave function psi is always just that E, right? Whatever state it's in, it has that energy. If I'm talking about a hydrogen 2s orbital, it's got a particular energy. If I'm talking about the 1s orbital, it's got its own energy, right? And those energies, if I measure that energy over and over and over again, if the electron is described by that same wave function, it's in the same state, I'm going to get the same value, okay? If the wave function is not an eigenfunction, then I can take that and find myself a possible expectation value, right? One way to say that is the wave function could be written as the superposition of some number of eigenfunctions, right? If I took enough eigenfunctions, I could get something that represented the function I've got. There are multiple possibilities for the measurable value, right? But what I get when I find the expectation value is that I find the average value of lots of measurements of that quantity. Okay, this is still useful, right? Because if I'm saying I think this is the wave function for this particular system, if I have a way to experimentally measure a property, I can see if the average of those values does get me the correct answer, right? And then I can become more confident that the wave function I've got is in fact telling me about the system that I'm trying to be looking at, right? That gives us a little bit more of the machinery for doing quantum mechanics, all right? In the next video, which I believe will close out module number 2, what we're gonna do is we're going to take some of these ideas and apply them to a real system. We're gonna do a little bit of looking at some quantities for the hydrogen atom, right? So we'll just start by declaring what the wave function is and work from there. But that'll give us a little bit of a vantage point on two things. One is how to actually do this for a real system, and the other is it'll be our first foray into being a three-dimensional problem instead of just a function of a single direction or parameter x that we've been doing. Thanks.